the last program, our two astronauts used trig ratios to work out the orbit and angle they needed to swing back on course. However, a more direct flight path could be calculated by finding this angle. But that would require solving an oblique triangle, a triangle with no right angle. And until now, we've only encountered situations with right triangles and solved them using the sine, cosine, and tangent ratios. For oblique triangles, though, we must develop two new tools, the sine law and the cosine law. We'll tackle the sine law now and the cosine law in the next program. Consider the oblique triangle ABC. No right angles. The angles are identified by capital letters. And the side opposite each angle is identified by the corresponding lowercase letter, side A opposite angle A, and so on. Let's develop some equations which describe the relationships between the sides and angles. Once this is accomplished, it'll be possible to solve any oblique triangle with only a few given values. We'll begin by dropping a perpendicular from angle A to a point on side BC. Call this point D. Let's make the length of AD H units. We now have two right triangles, ADC and ADB. In triangle ADB, the sine of angle B is opposite divided by hypotenuse, or H over C. In triangle ADC, the sine of angle C is H over B. Looking at the two equations, notice that there is an H in both. We'll reverse the equations so that the H's are on the left. In the top equation, multiply both sides by C. This gives H equals C sine B. Multiplying the second equation by B, we get H equals B sine C. We now have two values for H. So, B sine C must equal C sine B. Dividing both sides by sine B sine C leaves B over sine B equals C over sine C. The equation says that side B divided by the sine of angle B equals side C divided by the sine of angle C. It would seem logical then to assume that A over sine A will complete the sine law. Let's quickly prove this. Drop a new perpendicular from angle C to side AB at point E. CE is K units. Once again, we have two right triangles, CEB and CEA. In triangle CEA, sine A equals K divided by B. And in triangle CEB, K over A equals sine B. As before, we can change these equations to K equals B sine A and K equals A sine B. Therefore, A sine B must equal B sine A. Dividing both sides by sine A sine B, we get A over sine A equals B over sine B, which, as we proved earlier, is equal to C over sine C. This, then, is the sine law and can be applied to many oblique triangles. Now, how is the sine law going to help Ed and Charlie get back on course? Let's see what we know and what we need to find out. Probe 1's position is minus 4, 6. Let's call that point A. Probe 1 is trying to reach point B, where they will resume their course. Point B is at coordinates 6, 0. We'll need to find this angle, which we will call angle A. We'll call Capcom point C, and label the sides of the triangle A, B, and C. Let's substitute the values we know into the sine law equation. The coordinates of point B are 6, 0, so side A is 6. Now, we're trying to find angle A, so let's try to solve the A and B portion of the sine law. If we drop a perpendicular from point A and extend side CB to point D, we can fill in the lengths of sides AD and DC. Using the Pythagorean theorem, we can find the length of side B, 7.2. But because we don't know the value of angle B, we still have two unknowns, so B over sine B won't work. To use C over sine C, we'll need to know the value of angle C and the length of side C. The boys found angle C to be 123.7 degrees. Looking at right triangle ADB, we can find the length of side C using the Pythagorean theorem. Angle A is now the only unknown in the equation. The sine of 123.7 is 0.832. Dividing 11.7 by this, we get 14.06. Multiplying both sides by sine A, and then dividing both sides by 14.06, we get 6 over 14.06 equals sine A. Simplifying the left side and rearranging the equation, sine A equals 0.427. Angle A, then, equals 25.3 degrees.
Probe 1, what's your status?
Everything is under control, Capcom. We ought to be back on course and on our way to the center of the galaxy in no time. Okay, Ed. We set our new course for a heading of 25.3 degrees.
Roger, Probe 1. We'll check your progress from here until you reach Charon checkpoint.
That sine law is pretty powerful, eh, Ed? It sure got us out of trouble fast.
Yeah, I can hardly wait to get into more trouble so we can use the cosine law.